I take this board marker and place it 1.5 meters above the surface of the Earth. It experiences a force of gravity because there's two objects with mass. There's the Earth and there's the board marker. And Newton said that any two objects with mass exert a force of gravity on one another. But if I take this board marker away and put it in my pocket, that spot where the board marker was no longer experiences a force because there's nothing to experience it. There's nothing there. Right? The board marker was right there where I'm pointing right now, but now there's nothing there. There's nothing to be pushed or pulled. There is no force of gravity. But that doesn't mean that gravity itself has disappeared. What causes gravity fundamentally? We talked about this the other day a little bit. Einstein said it was the curvature of space-time. The Earth dents the fabric of space-time. Well, as long as the Earth hasn't disappeared, then the fabric of space-time is still dented. Gravity is still there. It's just not influencing anything. It's just not affecting the board marker at that point anymore. But how do we describe it? If we can't describe it as a force acting on the board marker, we have to have some other way of describing gravity. Hence the introduction of gravitational fields, the concept of gravitational fields. In general, we would say a field, gravitational or otherwise. There's other kinds of fields as well, electric fields, magnetic fields that you learn about in Physics 30. In general, a field is a region in which a force could be experienced by something. So there is a gravitational field surrounding the Earth. It doesn't mean necessarily that there is a force being experienced by a board marker, but if I was to put a board marker there, there would be a force. So it's a region in which a force can be experienced by an object. Now, specifically, a gravitational field is a region in which a gravitational force could be experienced by a mass, like a board marker, or like you, or like your desk. So the gravitational field shows us the influence of something producing gravity, like the Earth, whether or not there's something there to experience that. In order to have that gravitational field, all you need is the producer. All you need is that thing, that big heavy thing to dent the fabric of space-time. You don't need the experiencer. You don't need the board marker. To have the field, all you need is a producer, whatever causes gravity. To have a force, you need whatever it is that's causing it, the Earth, and something to experience or something to feel the field, like the board marker, like you, like your desk. So to have field, you got to have something causing it. To have a force, you got to have something causing it and experiencing it. If we take away the experiencer, we still have the field, because we still have that big object denting the fabric of space-time. Now, we would say that a gravitational field is a vector field because there's a direction associated with it, right? If I put this board marker in that gravitational field, it will experience a force in a very particular direction. It's not random. I don't put this board marker in a gravitational field. Sometimes it goes up, sometimes it goes down. It always goes down. So therefore, we would say gravitational field is a vector field, because not only does it influence things, but it influences things in a particular direction. Similarly, an electric field, a magnetic field that we deal with in Physics 30 would be vector fields as well, because they influence charges and magnets in particular directions. There are such things as scalar fields. An example of a scalar field might be like a heat field. Heat influences us, but not in a particular direction. So we focus, of course, this year on gravitational fields. Just know that a gravitational field has a direction associated with it. We define that direction, in fact, as the way that the board marker would move when it was placed in the field, or if it was placed in the field, which is down. Put the board marker in that field, it would move down. Therefore, the gravitational field points down toward the Earth. In fact, if we were to draw the gravitational field surrounding the Earth, it would look something like this. I put the board marker right here, it falls down to the earth. I put the board marker right here, where does it fall? Down to the earth. That's down, right? Like this is like Africa. Okay, this is somebody standing in Africa right now. Like if they drop a board marker, where does it go? Down. And from our perspective, it looks like it's kind of going up and diagonal, right? But from their perspective, it's down. So the gravitational field always points downward toward the center of the earth, toward the center of the producer. That's because every object that I placed in that field would fall down toward the center of the earth. All right, let's describe it mathematically now. There's two equations that we use, one of which we're going to focus on today. First one is what we call the producer equation. We use this one when we have information about what causes the gravitational field. So in other words, if we're talking about the Earth and the board marker, this equation would be used when we have information about the Earth. The equation looks like this. G, vector field, right, with absolute value signs around it, meaning we have a direction associated with this field, but this equation isn't going to tell me what that direction is. That's okay, because we know that the field always points toward the producer. So we know its direction before we even use the equation. But you couldn't get the direction from the equation even if you wanted to. It's equal to G, big G, times m over r squared. Not G m1, m2 over r squared, but rather G times m over r squared. Big G, of course, is the gravitational constant, 6.67 times 10 to the minus 11 Newton meter squared per kilogram squared. M is the mass of the producer, the mass of whatever it is that's causing the field. Again, the board marker and the Earth, this would be the mass of the Earth. The mass of the board marker would be irrelevant if you're using this equation. R is the distance from the center of the producer. So if I wanted to find the field strength at the surface of the Earth, then I would use R as the distance from the center of the Earth to the surface. If I wanted to find the field strength 100 kilometers above the surface of the Earth, then I would use the distance from the center of the Earth to the surface, and then another 100 kilometers on top of that. From wherever it is that you're trying to find the field to the center of whatever it is that's causing the field. And of course, G is the gravitational field strength. If it's caused by something, and the units for gravitational field are newtons per kilogram. Now, there are another set of units that you can use for gravitational field that we already actually have used without saying it in so many words. What do you think the gravitational field strength would be on average on the surface of the Earth? What do you think it would be? Take a guess at what the number for the gravitational field strength would be on the surface of the Earth. It does vary a bit. 9.81. We used to call that the acceleration due to gravity. But if I set the board marker right there, like it's not accelerating. So acceleration due to gravity it's not really a good way to describe it, right? It's not the best way to describe it, at least. If I take the board marker away, we'd still say the field strength is 9.81, but yet there's nothing there to accelerate now. This is a better way to describe it because this describes the gravity caused even if there's nothing there to accelerate, even if there's nothing there to experience it. Yep. So this is what we're going to do if we have information about the producer, which would be, in the case of the board marker and the Earth, it would be the Earth. Now, if we have information about the experiencer, in this case, with my example, it would be the board marker, then we're going to use this equation. G is equal to F over m. G is the gravitational field strength, once again in newtons per kilogram, or you could say meters per second squared, although now in this context we usually say newtons per kilogram, is equal to F. This is the gravitational force on the experiencer, which is the same as another term. What did we define as the gravitational force experienced by something? I'll wait for a minute until you guys can come up with the answer there. I'll wait for a minute until you guys can come up with the answer. I'll wait. Janae? It's the weight. It's the same thing as weight. So the weight of the experiencer. My weight is about 700 newtons. So we would say my gravitational force is 700 newtons. If I wanted to find the gravitational field given information about me, then I would say the force of gravity would be 700 newtons. M is the mass, but it's the mass this time of the experiencer. And that's going to, of course, be in kilograms. Force is in newtons, mass is in kilograms. And once again, the units for gravitational field would be newtons per kilogram. So, if you know something about what's causing the field, use the first one. If you know something about what experiences the field, use the second one. What if you know something about both? Okay, let's say I got the board marker in my hand here, and I know the force and the mass of the board marker, but I also know the mass and the distance from the center of the Earth that I am. What if I know enough to use either equation? What should I do? Doesn't matter. They should both give you the same answer, right? If the field strength caused by the Earth at this particular location was, let's say, 9.79, then what do you think the field strength experienced by the board marker would be? 9.79, right? Whatever the field is caused by the producer, if there's an experiencer there, would be experienced by the experiencer. So if you know more about this, use it. If you know more about this, use it. If you know enough about either one to use either one, use whichever one you want. Use probably the second one because it's the easier equation, but whatever one you want should give you the same answer. We're going to do one example, and then we're going to give you a couple questions, and we're going to wrap it up for the day here. By the way, the table that I just flipped past there, quickly flipped past, I'll go back to it just for a second. This is just a bunch of data for the mass of planets and moon and the sun and so on, and then the equatorial radius. The equatorial radius just means the distance from the center of the planet or the sun or whatever to the equator, which is important for us sometimes because we need to know the distance from wherever it is that we're trying to find the field to the center of the object. You're not going to have to memorize any of these numbers, of course. Okay, if you need, some of them are on your data sheet, some of them are not. If you need something that's not on your data sheet, then we'll give you a table or we'll bury it in a paragraph or something that you'll have that information available to you. But sometimes in the questions that we work on in class here, we have to refer back to this table. First question says, calculate the magnitude of the gravitational acceleration, which is, what's another name for gravitational acceleration? What's the new gravitational acceleration? We're calling it gravitational field now, right? I mean, if you called it acceleration, I wouldn't mark that wrong because it's right. But we tend to call it field from here on out. Of an object at the equator of the surface of the Earth and the Moon, and then determine the ratio. We'll worry about that later on. Let's say that we want to find the field strength on the surface of the Earth, the surface of the Moon. You want to find it on the surface of the Earth. You know something about the Earth, right? You know the radius of the Earth, the mass of the Earth. Is the Earth a producer or experiencer? Is it causing the field or experiencing the field? I'm on the surface of the Earth right now. I'm on the surface of the Earth right now. I'm that person. That's a big person, eh? I'm that person on the surface of the Earth right now. What produces, what experiences the field? There's the Earth and there's me. Who's causing the gravitational field there, really? The Earth. Who's experiencing it? Me. So we know more about the Earth than we know about me in this question. So let's use the producer equation. Say gm over r squared. It's 6.67 times 10 to the minus 11 Newton meter squared per kilogram squared times the mass of the Earth, which is on that table that was on the previous page, 5.97 times 10 to the minus 24 kilograms, divided by r, I forget what that distance is, the radius of the Earth, 6.38 times 10 to the 6. The distance from the center of the Earth to the surface. Let's figure out what that value is. What do you expect that value is going to turn out to be? Take a guess. Riley, take a guess.
9.81.
It's going to be either 9.81 or close to that, right? It's different everywhere on the Earth, right? But it's going to be, on average, about 9.81. So if we get a number that's close to that, we're probably right. If we get a number that's way off of that, then we're probably wrong. 6.67 times 10 to the minus 11 times 5.97 times 10 to the 24. Divide it by, let's do some brackets here, 6.38 times 10 to the 6. And we square that. We get 9.78. Does that seem reasonable? Sure. That's pretty close to 9.81, right? We're going to call it newtons per kilogram. But if you wrote it as meters per second squared, that would be okay as well. Just because we're kind of shifting the way we think a little bit doesn't mean that all the stuff that we've done so far is wrong. We're just dealing with it slightly differently. Now let's find the field strength caused by the moon. I think it's more or less. I think it's going to be higher than 9.78 or less than 9.78. Pretty? Less. Quite a bit less, right? Gravity we know is less on the moon. 6.67 times 10 to the minus 11. Bree, why do you think it's going to be less? Okay. It's like saying it's a circle because it's a circle. Yeah. Yeah, it weighs less, right? The mass is less. The moon has a mass of 7.35 times 10 to the 22. About 100 times less than the mass of the Earth. And the radius of the moon is 1.74 times 10 to the 6. Now, the mass is smaller, which you would think would make G smaller. But then the R is smaller as well, which would actually make G bigger, right? So maybe we find that R ends up being a bigger factor. Let's see here. I think when we do this, we get about 1.6. Oops. Sure enough, we get 1.62. So Bree was right. She expected a smaller value, and we got a smaller value, quite a bit smaller. Now, we want to find a ratio of this to this. If we go into my imaginary book, my imaginary physics thesaurus. You guys know what a thesaurus is? A book of synonyms, right? A book that has words that mean the same thing as other words. If I go into my imaginary book of physics, my imaginary physics thesaurus, because I don't really have one, and I look beside ratio, what word do you think would mean the same thing as ratio? I'll tell you one, compare. Compare means the same thing as ratio. If you want to compare two things, what do? Mathematically, that is. Divide. Compare, divide, ratio. You want to find the ratio here? Let's say 9.78 to 1.62. Gives me 6.04. So my ratio would be 6.04 to 1. All right, I want you to work on these three questions on page 218. The data table is there for you as well. Just a couple things that I want to point out here. Say question number 1, for instance, says a satellite orbits Earth at a distance of 3r above the Earth's surface. What does that mean? Like, what are they telling me in that question? Yep.
3 times the radius of Earth.
Yeah, right, above the surface. So what value of r would you end up using for this question? 4 times the radius of the Earth, right? Because you need the distance from the center of the Earth to where the satellite is, so it would be 4 times the radius of the Earth. Does that make sense? Okay, I'm not sure if we come across that anywhere else or not. Yeah, number 3, 6.6 times the radius of the Earth. Once again, 6.6 times whatever the radius of the Earth is. This time it says it's orbiting Earth at this distance from the Earth's center. Would we have to add 1r to that? In other words, make it 7.6? No. Question number 1, it's above the surface. You have to add the radius of the Earth. Number 3, it's from the center of the Earth, so you don't have to add anything to it. You're given the value already. You just have to multiply it by the radius of the Earth. That's for